Yeah, hello and a warm welcome from our studio here in Karlsruhe. My name is Adrian Fiege, and today in our online seminar we will talk about sample preparation. And with me is Frank Portala.
Hello, also warm welcome from my side.
So let's dive right into this presentation. So we have prepared quite a lot of things for you which we will cover today. So we will start with a little bit of an introduction about XRF, also some basics about sample preparation. And then we will spend quite a lot of time in the lab today with Renata Janic, who will guide you through some best practice examples, for example. We will talk about liquids, powders, and pellets. Then we go back to the studio here, talk about the effects of grain size and matrix. And we will tune back to the lab for fuse speeds and also some larger samples, so small spot analysis. Type in your questions at any time, and later on we will answer them during our Q&A session. Just for those who are relatively new to XRF, Frank, here I have a little bit of an overview of what XRF is. So XRF is a method where we have an X-ray tube that excites the sample. And what happens is that we kick out an inner shell electron, so very close to the atomic core, out of the atoms. And then as a next step, some outer shell electrons fall into the vacancy. And this emits characteristic X-rays. And these X-rays can then be detected, so based on their wavelengths or energy. If you want to learn more, we have some educative videos online. And maybe, Frank, you can briefly cover what kind of instruments we offer.
Yes, sure. So these physical principles are valid for all our XRF instrumentations, and we offering from small compact benchtop ED-XRF analyzer, such as the S2 Puma and Polar, via an benchtop WD-XRF instrumentation to the full floor standing instrumentation, including simultaneous instrument. And if you look at the instruments itself, the key of it, when you do generate some analytical data, is the analytical accuracy and precision. So that should be as high as possible for both information. And this is quite important if you look at the various samples which exist. And here we are able with XRF to measure really quite a lot of different samples, such as liquids, powders, granules, pellets, solids, bulk samples, metal samples, for example. And all of them require different sample preparation. And this is important to consider. And this is especially the topic of this seminar, to cover the best sample preparation for these type of samples.
Yes, exactly. So as you can see, we can really cover a lot of samples. And of course, it matters which sample type you have, if it's a powder or liquid, how much sample preparation is needed, and also how much care needs to be taken to get accurate and precise results. So one thing we have to consider when we talk about analytical equipment, that yeah, the analytical equipment can be super precise. But if we don't get the right representative sample, then what does it matter? And that's exactly what Frank said about analytical precision, accuracy. So we need to be having both under control. So especially in mining, we're talking about huge tons of samples, and we want a representative analysis of that sample. So the first thing, we have to make sure that we have a good sampling, good sample homogenization, and then only we can get a representative result. And here especially the preparation plays an important role. So of course, that pyramid is just a bit an indication. It's how much sampling, sample pre-processing, let's say homogenization, breaking of samples, and preparation matters for the ultimate analytical precision. And accuracy depends really on the material you're measuring. For instance, if you might measure a steel plate, yeah, cutting that steel plate is not gonna make a big difference. If you have a very homogeneous process, then your sampling and preparation has a relatively small effect maybe on that. Yeah. Quite different if you're starting from a rock sample, for example. But the effect of representative sampling ultimately and reproducible preparation can be very large compared to the impact of the real analytical precision and accuracy.
And this is for liquid samples, for example, you would consider they are often very homogeneous. And then the sample preparation is really straightforward. Taking a sample, preparing it in a liquid cup, ready for the analysis. But also for liquids, there could be some exception. If you look, for example, at crude oils, they have some particles in it, so you have to think about how to handle that, how to get an inhomogeneous sample. It's more homogeneous, so by adding certain things, preparing it with chemical steps. All of this will be covered in detail more in our session with Renata in our laboratory. And so we would like to switch over to her in this first session there. Thank you.
Hello and welcome to our lab session today. My name is Renata Janic. I'm an application scientist for XRF. And with my first session today, I will start with the preparation of liquids. So in general, to prepare liquids is very easy. It's the easiest way to start a measurement with XRF. So you will just have liquid samples, for example, like a mineral oil sample. You transfer it to a liquid cup and you can start the measurement immediately. But now I would like to show you a little bit more detailed what it's important about the sample preparation of liquids and maybe how to handle a little bit more difficult samples. So I already prepared something here, so let's have a closer look. So there are different liquid cups available. So it's mainly the difference is the diameter of the liquid cup. So you have big liquid cups. So the most common liquid cup is the one with 35 millimeters, which can be used for the 40 millimeter sample cups. But in case you also have smaller amount of samples, there are also smaller liquid cups available with diameter down to 8 or 10 or 6 millimeters. So what about foils? Of course, you need a foil to prepare the sample. So there are also different foils available in the market from different suppliers, different foil materials, and also different foil thickness. The most important is what is the chemical resistance, so what kind of foil you need for your material. So the two most common foils are the Prolene foil and the Mylar foil. There are also different type of shapes. So the, let's say, the most cheapest foils are the one from the rolls. I think that the most of them you do have in the lab. So here you can just cut it or you can remove the foil from the roll and then you have to prepare the sample. These are the samples which we use in our lab. So it's very easy to disassemble the cup. So we have three parts, an inner ring, an outer ring and a lid. So we do have this nice preparation tools for liquid cups. But if you do not have this, of course, you can also use the cup of your system. So I will just use this one. So it's very easy. You will just put the foil on here and you can assemble the cup. Always important, don't touch the area of the measurement. So, or do not contaminate the foil like I did it here to put it somewhere on the lab bench. These rolls sometimes are a little bit difficult to prepare at the beginning. So you need some training. And in general, in my opinion, you always have a higher consumption of these foils. So this is one type of foil. There's another type of foil. These are the pre-cut foils. So this is a little bit easier to prepare. So you have this foil on a tray, remove it from the tray, and then prepare the sample. And there's also possibility of foils on a tray. This one I really like the most because it's the easiest way to prepare a sample. Of course, they're a little bit more expensive, but it's very easy and you do not touch the surface of the sample area. And that's it. So it's very easy to prepare the liquid cup. You should always make sure that the surface of the liquid cup is flat, that you do not have any wrinkles. And also you should make sure that you do not have any, for example, some cups do have some sharp edges that maybe can already cut a little bit your foil. So this will maybe lead to some problems when later on analyzing the sample. So make sure the foil is clear, don't touch it. And I always avoid to put the sample somewhere to avoid any contamination. So this is the reason why I like to use this tool. what kind of foil do you have to use? So first of all, you have to check the chemical resistance of the foil, of your material. So typically you will find a lot of information about this on the homepage of the foil supplier. So in general, you can say Prolene foil can easily be used for mineral oil samples or for water solutions. The Mylar foil is typically used for example, kerosene, diesel samples, and it's more resistant for this kind of material. What about the thickness? So typically the most used foil for Prolene is the 5 micron foil, and for the Mylar 3.6 microns. Of course, you can have thinner foils or thicker foils, but always I think these two thicknesses is a quite good compromise between stability and also absorption for light elements. What is also important to know about the contamination. So each foil do have some contamination. So typically you will find this information on the box from the foil or also on the homepage of the supplier. In general, the Prolene foil is a quite clean foil, so we do not really have issues with some elements for contaminations. From time to time, I see a very, very low signal of alumina, but typically for the Mylar foil, the most critical elements are calcium and phosphorus. So you do see a clear peak for these two elements. So if you want to analyze calcium or phosphorus, for example, in loop oil samples, it's better to use the Prolene foil. So then you do have less contaminations. These contaminations can also vary from lot to lot. So if you have a new lot of sample, you should make sure that at least maybe you can define a blank in your software. Then you can just check it with the news foil from the lot that the blank is more or less the same. Otherwise, you can correct this blank by the software. So this about the foils. And so typically it's very easy to prepare sample if the cup is prepared. You have to balance the sample. We use for these 3.5 centimeter cups, we typically use about 7 grams of samples. You should make sure that the cup is at least filled half with the sample and not to have only 1 or 2 grams of sample. So this will affect also the intensity, and we will also talk about later about information depth of the sample. So therefore you should make sure that there is enough sample in your cup. So for a mineral oil sample, I have to balance the sample. So to avoid contaminations, I just use this weighing paper, put it on the balance. It's also not necessary to use a big analytical balance, so we use these small balances. You should fill in 0.1 plus minus gram of sample to be also reproducible. And so you can use a pipette or this one-time disposal pipettes, and then you just fill in the sample into the liquid cup. Transfer it to this. So now I need a lid. Here it is, and that's it. Yeah. So you see, in the sample is ready to be analyzed. A mineral oil sample is a quite clean, homogeneous, and easy sample. So what about samples which are more critical? Yeah. So or maybe which are not homogeneous or which are solid? How to prepare these kind of samples? So I already prepared something here. So a very common sample for petrochemical area is, for example, a grease sample. So you see it's a solid, greasy sample. What you can do with such kind of sample, of course, you can transfer it to a liquid cup, but this is quite tricky, and you typically also have a lot of bubbles at the bottom, which is not really the best way. So here you can try to use the sample as it is. There are different possibilities. You can use, for example, such a tray. Yeah, so you can prepare this on your own with some borax, or you can also buy these kind of grease cups, I call it. So you will just use some grease sample. We'll try this to do it now. Put it into the cup. Flatten the sample. And of course, you also have to weight the sample. So what is the mass of the material which was used? And then this you can just transfer to a liquid cup. I will prepare one just very quickly. And then you can transfer this grease cup into a liquid cup, and you can start the analysis. So this is one way to handle grease samples. But there are also some other materials. Here I do have some palm oil. So you see this is a solid sample. Typically, what we do with such kind of sample is we do heat up the sample until they get liquid. You also have to homogenize these kind of samples, and then you will just transfer the liquid into the liquid cup. If the sample is quite inhomogeneous, if you even also have some particles in your sample, so then you just have to be quick. Yeah? So you have to heat up maybe the sample to homogenize, or you mix it manually, or you can use a vortexer or a stirring plate, and then you just transfer the liquid sample to a liquid cup and start immediately the measurement. For inhomogeneous samples, or if you do have some particles which are settling down while the measurement is running, it really makes sense to reduce the measurement time. For energy dispersive samples, you will maybe have typically a measurement time of 60 or 100 seconds. So, but for such kind of sample, I recommend to have maybe only 30 seconds of measurement time to reduce the effect of the sample preparation, or by settling the particles in your sample. So this is now the part of the sample preparation about liquids. So I hope I have not missed something. In case you have any further comments or questions, please feel free to contact us or to contact me. I'm always happy to get some ideas from customer how to improve sample preparation. So now let's go back to the studio, and meanwhile I will just rearrange things about pressed pellets. So thanks a lot. See you later.
Yeah, thank you, Renata, for showing us how to prepare liquid samples and give our audience some tips and tricks. And now, while you're setting up for the next session, we would like to spend a few words about grinding of samples, so of preparing powder samples. Here, of course, we need to take care again about the sampling, depending on what material we have, and then grinding has a significant effect. And why is this the case? So the background behind that is depicted here in this little sketch. So first of all, we have a tube down here which excites our sample, and that sample is then emitting X-rays. And the detector, however, only sees a certain part of those emitted X-rays. So in essence, we have a certain analytical volume here, kind of indicated by 3, that is basically seen by the detector. And then we have a sample thickness that might differ from that. So if it's thick enough, then all is good. If it's not thick enough, then some corrections need to be applied. This is what Renata referred to about how much liquid samples we put inside. However, what's especially crucial about solid and powder samples is the information depth, or also sometimes called critical depth. And so the critical depth in a sample means that we only get the information out of a certain depth within the sample. So some X-rays, fluorescence X-rays, are basically absorbed. And so the information depth is higher in lighter materials like graphite, and less significant in heavier materials, denser materials like iron or steel, for example. And then also it is higher for heavier or higher energy lines, like for example cadmium K alpha, and not so much, we're talking only about an information depth of a few microns for lighter elements and low K alpha lines, like for example magnesium. So especially for those, it's very important that we prepare the sample in the right way, right, Frank?
Exactly, yes. And especially if you then grind a sample, there the grinding time is an important parameter which needs to be optimized. At the beginning, when you are using shorter grinding times, all the particles are larger in size, and then they are not so compact in this information depth. And while the grinding time is increasing, the particles getting smaller and smaller, and then they are more compact in this critical depth or information depth. So by having a more compact layer of particles, it also means it increases the intensity of your sample. And this is shown here in this example on a silica line for quartz sand. And here, with a longer grinding time, you see an increased signal voice. And that's what we observe. At a certain point, there is a plateau, so it makes no sense to increase it too much, but you have a significant impact if you increase the time from 10, 20, or to 60 seconds.
Yeah, exactly.
And here is an overview about the different materials for grinding samples. So you can grind a sample in stainless steel material, but you have to consider, because stainless steel is not so hard, and you have some impact from the steel material of your grinding cast into your sample. So you somehow have a kind of contamination. And there are more harder substances used for grinding material, like zirconium dioxide or even tungsten carbide. They are higher in price, I have to admit. But on the other hand, you have maybe an impact of more rare elements into your sample, and then it's easier to measure your sample appropriately.
Yeah. And I think now Renata should be ready for the second session and explain us more about grinding and also press pellet preparation.
Hello and welcome back to our next sessions about powders and press pellet. So to prepare a press pellet, we need to have a fine powder. Typically for XRF analysis, we do want to have a grain size of about 40 to 50 microns. So this means in the first step, we have to grind the material to get a fine powder. How to grind the sample and what is important, this is something I would like to show you now. So first of all, we do have different grinding vessels here. So the easiest way to grind a sample is really to do it manually. So you can really do it with some kind of ahead vessels to grind it manually. This can be used if you only have a few samples you want to analyze. The easier way is to have a grinding machine. So there are different grinding machines available in the market with different techniques and different vessels. So if you want to use or if you want to grind a big amount of samples, like maybe 50, 100 or 200 gram, you can have these big grinding vessels like we have here. If you have less material to grind, so typically for one pressed pellet we use about 8 to 10 gram of material. So with this grinding vessel, typically we grind about 20 or 30 gram of material. And there are also ball grinding vessels, which of course have less material. You can have one ball or maybe a few smaller balls which are used to grind the material. Doesn't matter which technique you use, there's always something, let's say you have to think about the material itself. So typically what we have in our lab here is a tungsten carbide vessel. So this is the most expensive one, but it's also the hardest material. So with this material you can grind, let's say, all material which are typically in the lab. There are also steel vessels available, which are a little bit less in price, and also ceramic vessels. So you have to think about the hardness of the material you want to grind, but depending on the vessel material, you also have to think about contaminations. So if you use a tungsten carbide vessel, you will always have a few ppms of contamination of tungsten or cobalt. If you use a steel vessel, then of course you will have some contaminations of iron or maybe nickel and chromine. This you have to take into account if you want to really do trace analysis for these kind of elements. Then in this case, I would like to avoid material which will lead to contaminations and will also affect your results. Typical grinding times also depends on the technique you are using. So we have a swing mill here in our lab, which typically has grinding times between 30 or 60 minutes, which is really short. If you have maybe another grinding device, you can maybe have 60 or 120 or even higher measurement time in seconds to get a fine material. So this means the grinding time really depends on the device you're using. If you get sample like this, which is very coarse, so we have to grind them to a very fine powder. There are different ways how to analyze this. So if you have a very fine powder, you can also put it into a liquid cap and you can start the measurement immediately. So this is a very nice preparation if you just want to have maybe a standardless analysis of a powder. And so this is the easiest way to prepare the sample and to run it in a liquid cup. If you want to prepare a pressed pellet, then of course you have to add also some binder. There are different ways how to do this. So here I have already grinded some material in our vessel. There's the possibility to grind the sample without any binder, but there's also the possibility to add a few grinding aids into the powder and grind the sample with a grinding aid. So the grinding aids, they are typically also wax and cellulose based. There are different grinding aids available in the market. For this amount of samples, maybe you add about 2 or 3 taps of the grinding aids, and this will also improve the results for the grinding and is also kind of a binder, so you can press the material immediately. After the sample is grinded, then this is now the most dustiest part, so you have to remove the powder out of the grinding vessel. The tungsten carbide vessel is also quite heavy, so then you have to get rid of the powder out of the vessel. And depending also of the material, or if there is also a little bit humidity in the material, it can also stuck quite well to the grinding vessel and here to this material. So you can remove this. So I do not have gloves now, so it's nothing dangerous. And you see it's quite dirty and it's also a little bit sticky. So what is the best way to clean this? So depending on the material, you can use some water or use some ethanol to clean the vessel. What we do quite often, we use some quartz sand. I just fill in some quartz sand into the grinding vessel and just start a new grinding for about 30 seconds to clean the vessel with the quartz sand, and then you can clean it with some water. So after the sample is grinded, so we talked about the grain size. So the most important thing, it's not if it's always 40 microns or 50 microns. The most important is if you decide for one grinding time, you should always prepare the sample in the same way. So if you decide for 30 seconds grinding time for every sample, then please use the same grinding time. Otherwise, this will affect the analysis or will change the intensity of the sample. The sample now is without any binding, so you can run a liquid cup measurement, or if you want to prepare a pressed pellet, you have to transfer the sample to this mixing container. This is what we use here in our lab. I added some wax as a binder. So the most common binder is some wax, paraffin wax, which is used. Typically 10% of wax is used for a pressed pellet, so this is enough. There are some materials which are a little bit harder to be pressed to get a stable pressed pellet, for example, some coke samples or titanium dioxide or pigments. In this case, you just increase the amount of wax to get a stable pressed pellet. After everything is transferred to the container, you have to homogenize, you have to mix the sample. You can do it manually by mixing, but we also do have here a small vortexer where I can fix the container, and then you can just mix it for maybe 30 seconds until everything is well homogenized. Now the powder is ready to be prepared as a pressed pellet. To prepare a pressed pellet, of course, we need a pressing device, and the same like for the milling devices. There are different devices available in the market. There are small tabletop presses, even manual one, which you have to pump manually. So they typically go up to maybe a pressing force of 10 tons, but there are also semi-automatic tabletop presses available. And of course, you will also get these big presses, fully automated, they're also available. So it depends on how many samples per day you want to prepare, of course, of your budget. And so therefore you have to decide which press is the right one for you. Yeah. So here I already prepared a few press pellets. I would like to show you which ways a sample can be pressed, maybe what has to be taken into account. So this is what I would like to show you now. So here I do have different pressed pellets. So in general, you can press the sample in an alumina cup. Yeah, so here there are also different cup shapes available. It depends on your pressing device. So the advantage of the alumina cup is you can press the sample, you can store the sample very easily, you can mark and sign the sample, so therefore the alumina cups are quite nice. If you just run the sample once and then you dispose it, so you can also prepare it without alumina cup. So here the sample is just pressed with the sample itself and with a binder, and so it's not necessary to press it into alumina cup. But here the sample should be thick enough to get a stable sample, so at least you should use 10 grams of sample to get the thickness of the sample we require and also that it's stable enough. If you have less material, yeah, so there's also the possibility to press the sample on a bed of borax, yeah, so we do not use boric acid anymore. So here you do have the possibility also, if you have less sample, maybe only 5 grams of samples, so you can press it on a bed of borax to get a thick and stable sample. After each pressing, I recommend really to check, is the sample stable? So the press pellets are always analyzed under vacuum, so in most of the cases. And so you should make sure that the sample is stable, that it will not crack under vacuum, and that you do not have a lot of dust on your sample. I do it in a very easy way. I just check it by clicking on the desk. And if the sample is still stable and if there is no dust anymore on the sample, you can be sure that the sample is stable and can be used for the analysis. What about samples which are maybe a little bit hard to press? So I told you the easiest way is to increase the amount of binder to get a stable pellet, but there's also the possibility to have a very thin layer if you only maybe use 1 or 2 grams of samples. So here I also have a bed of borax and a very thin layer of samples. So here I have a very nice pigment, so it's a very nice red color to see the difference that it's a very thin layer. So this is also one way how to prepare maybe only 1 or 2 grams of samples. If you have even less material, maybe only a few milligrams, let's say maybe 100 or 200 milligrams, there are different ways how to do this. So the easiest way is to use the small liquid cups. So here I used a liquid cup with a diameter of 10 millimeter. And so here you can easily use it for 50 or 100 milligrams of sample. The big advantage of this preparation is that you can reuse the sample again if it's maybe some development and you would like to reuse it for some other techniques. So this is the easiest way. If you want to prepare a press pellet, so we have a little tool in our lab here. So here with this 10 millimeter diameter, I can make a little hole in the borax. So you just use the borax sample, press a little bit the tool into the borax so that you get a little hole. And then you can just fill 100 milligrams of sample to the center of the sample into the hole, and you can press it. And then you have this small press pellet. Of course, you cannot reuse the sample again, but you will maybe improve your analysis. If we work with small diameter, of course, then you have to use a smaller mask on your system to cover only the sample, like here. So here we have a cover of our sample cup that you can run the analysis. If you do not have a smaller mask, of course, you can use the bigger diameter, but then you have to take this into account when evaluating the sample. So this is what I would like to show you for the press pellet. And in the next step, I will show you how easy it is to prepare a press pellet. So now we are going to press the sample which we have mixed before with some wax as a binder. So let's start. This is the pressing tool, so the only thing you have to do to fill in the sample. If you want, you can use alumina cup, but I will do it now without an alumina cup. To avoid sticking of the sample onto the lid, so what I really like is these pellet dice films. So you can just put it onto the lid to keep the lid clean and to avoid sticking. So we only have to close. To start the measurement, I just have to push the green button. So here our measurement program, which I use at the moment, is 50 to 15 tons force and 10 seconds pressing time. In general, it's not so, I mean, you already get a lot of information about pressing, how the pressing force will affect the intensity of especially light elements and also the pressing time. So it's not so critical if you use 15 tons or 20 tons, or if you press for 20 seconds or 30 seconds. The most important thing is that you always use the same parameters. So if you set up a calibration with your standards and if you run unknown samples, you should always use the same sample preparation parameters. Not only for press pellets, the same for grinding and also for the fusion. So just to keep the effect and the error of sample preparation as low as possible. Yeah. So here, this press is also available with different pressing tools. So if you want to press smaller diameter, this is available. Or for example, if you want to press these rings, like they are also used typically for automation. So there's also a pressing device available to prepare the rings. So it's quite nice. There are also different presses available. Maybe you also know the very simple one, the manual one, which you have to pump to get the pressing force. Of course, these presses can also be used, which are maybe more suitable if you only have a few samples per day. But if you have a press like this, where you have a defined force and defined pressing time, this is also good to keep the effect of sample preparation low. So the pressing process is finished. Now I can open the door and the press pellet is now here. Due to the fact that I used the foil, I just have to remove the foil and then the press pellet is done. So thanks a lot, and now let's go back to the studio.
Yeah, thank you very much, Renata. And we would like to continue now with press pellets and more details on these. So after while the grinding is going on, it's quite important to have smaller particles. And with the smaller particles, you also have a more condensed sample later on after pressing them. So the information depth, the critical depth, is smaller and more compact, and this is an advantage because it results into a higher intensity and a better reproducibility of your measurements. Here on this slide you see the advantage of having an press with a certain power, and this results into a more stable pressing. And for the different elements it's shown here, the effect on using a different pressure. But in general, a pressure of about 15-20 tons is more than sufficient for many samples. You often do not have to use the full power of a certain press.
Yeah, so even a smaller press is often sufficient, and it depends a bit on your throughput. And you can also see a bit that the effects differ a bit from element to element.
And here, this slide shows quite good if you have an inclusion in your sample, and that's really sometimes possible with pressed pellets, because sometimes it's not possible to grind all particles in a sample to the same size, and then somehow you have to deal with these inclusions. And of course, this has an impact on the reproducibility of your sample, because sometimes there could be more of them in it, sometimes less. And if they vary from one pressing to the next one, of course, that has an impact.
Yeah. So these inclusions can have significant effect, like Frank said. So this is also called a mineralogical effect. If we have minerals of different type in our sample, it essentially results in more scattering from pellet to pellet, because you can't break down these crystals completely. If they have preferred orientation, they interfere with the beam essentially, and that means you have some for the same material, maybe a bit higher intensity or a bit lower intensity for certain elements. This might be completely fine for your application because you still get the right results, but it might also mean that for some, if you want really high precision, that you need something else in terms of preparation. This then brings you to fusion preparation, where you essentially break down the matrix and break down the elements and the minerals and oxidize them into oxides. So for instance, an albite would be distributed into sodium oxide, silicon oxide, and aluminum oxide.
Yeah, and this brings me to the fuse bead preparation. So you take your sample, sometimes an igniting is needed. This means you heat it up to a certain temperature, often in order to reduce water in it. You fill the sample and mix it in your crucible. Some samples requiring oxidizing, and then finally you melt the sample, and then you move it over into your casting and cooling process. And this shows you in detail how the fusion process looks like. So from oxidation to decomposition, and then to the fusion itself with melting and mixing. And then also quite important, and the step of cooling down in a proper way to finally have a nice looking fuse bead. This shows you an fusion bead preparation. The sample is already in the oven and is now removed. You see the glowing crucible and how the sample is pulled into the mold. So everything went smoothly here. And now the cooling step starts. And then at the end of the process, ideally, you have a nice looking fuse bead.
But with fusion, as you can see, there is a few more steps involved. And as you can imagine, compared to just grinding a sample and pressing it into a pellet, more things can go wrong. Here are some examples of what can go wrong. For example, you can have vesicles, bubble inclusions in your fuse bead. This typically means the viscosity was too high, temperature maybe too low, fusion step too low. This would interfere. Crystallization is a thing that can often happen. Mooning could happen. I will come to that later. And also a couple other effects can happen. But there are ways to overcome this. And here I will just provide a few examples. So first of all, for your material that you have, there's always a sort of ideal cooling path. So for example, you want to stay in that glass formation zone, and you want to stay well in that glass formation zone along the orange arrow here. You don't want to cool too fast, that would cause cracking, or you don't want to cool too slow, that would cause crystallization. Other things that can happen is your fuse bead might stick to the mold, and you might face a situation where this cannot be overcome by simply changing the recipe, because that's simply your sample. Then you can add some additives. They are so-called non-wetting agents, where you still want to make sure that you still produce a nice flat sample. So if you add too much or too little, you can cause effects like the mooning that we've seen on the previous slide. There are other additives which are important. One of the most important ones probably is oxidizers. If you have not fully oxidized materials, metals in your sample, or sulfides, for example, then you need to oxidize those. This is important also to protect your platinum ware, because otherwise this can corrode and interfere with your platinum and even destroy it. Don't have to worry about it, just apply the right oxidizer to it. For instance, this is important for copper ores when you want to oxidize them. Another thing is maybe sometimes you have reasoning for reducing the melting temperature, for example, to reduce the melting time or reduce the amount of volatiles lost. Then there are additives. Another thing that's maybe nowadays a little less common is heavy absorbers to reduce further matrix effects. This is normally dealt very well with our software.
So there were quite some steps necessary in order to get a nice looking fused beads. And then when you proceed and finally you measure your fuse speed, it's also important to handle them properly. And that's shown here. So for example, if you accidentally hit them or touch the surface of your fuse bead with your finger, shown for example for a sodium and light element signal here, at the beginning on number 1 you have a very low intensity, but once you have touched it, the intensity increases due to the fact that often sodium chloride is in the water on your finger, and then it's getting even worse in step 3 here when you have done it a second time, touched it a second time. But as you can see, cleaning processes are quite important and can be done, and you get a quite low level after cleaning it with distilled water. So avoid touching the surface. Use gloves when you're transporting and handling the fuse bead. Also, don't put the fuse bead on the lab bench. This all has an impact on the surface.
Yeah. Of course, there are also elements where this doesn't matter so much anymore. This comes back to the discussion about the penetration depth we mentioned earlier. So for instance, the fingerprint on the sample doesn't affect your calcium signal. But you can, of course, also have other contaminations from your working bench or desk that can affect even a calcium signal.
Yeah, and with this, we would like to summarize the fuse bead and pressed powder preparation. No doubt about it, pressed powder preparation is really fast. It is on a low cost level. You nearly have no dilution because you only add a very few amount of binder, for example, but you still have to live with the mineralogical effect if you prepare pressed powders. On the other hand, for fuse beads, the preparation takes much longer. You have a higher dilution factor, which means it's more difficult to measure traces and on a low concentration levels. But at the end of the day, you really remove the mineralogical effects, which means you have a more independent calibration. The calibration on your system is more robust. You maybe can take samples from different mine sites. Even that's more stable, for example. Also, you can use the calibration for wider calibration ranges. Yeah. And with this, we would like to hand back to Renata in the laboratory. And she now would like to show you more details on the handling and tips and tricks for the fuse beads. And later on, she will show you also some more details on mapping and how you handle such samples correctly in an XRF spectrometer.
Hello and welcome back to our next session about fusion and preparing fuse beads. We already got a lot of information from my colleagues about the fusion process, so here I would like to focus a little bit more about the handling. Of course, as for the grinding devices and for the pressing devices, for fusion there are also different devices available, mainly gas-based or electrical devices, and based on the system you're using, maybe you will also have to use different fluxes, so different mixtures are available with additive or without additive. So it also depends on the material you are going to prepare as a fuse bead. But in this case, the best way is to contact your supplier, and they will prepare the right recipe for you. Here I would like to focus a little bit more on the handling of the crucibles and maybe what's important to know. So of course, for the fusion device, we need these platinum crucibles, like the one I do have here. And we have the casting molds. Here we have a very nice tray to transport and to keep the crucibles in a nice way. it's of course important to really work carefully. They're made of platinum, they're very expensive, and so you should always work carefully, and you should try not to store them in a very nasty way that they will get scratched or something like this. To prepare the fused beads, it's also not very difficult, so we do have some kind of flux. Typically, for this device, I will prepare a fused bead with a diameter of 4 centimeters. So I will use about 9 or 10 grams of flux, and I will mix of about 0.8 or 1 gram of sample to prepare the fused bead. So it also depends from the recipe. But it's important here, you should really use an analytical balance to balance the weight of flux and the sample powder. Some powder can be used as it is. Some powder has to be ignited first. It depends from the material. But here I have to balance. I will do it now manually here without the balance. I will put in some flux into the crucible, and then I will put in some sample material, maybe 0.5, 0.8 or 1 gram of sample. It depends on the material. You can gently mix it manually, or you can use a spatula, but you should make sure that you're not scratching the platinum crucible. Just mix it gently to get it homogenized. And now the sample is ready to for the fusion process. Yeah. So then the fusion process is finished. The sample is now poured into the molding casting mold. Sorry. To remove the sample, you can use this little tool, just a little sucker. So you can release the sample out of the mold. If you do not have a sucker, of course you can do it manually, but you should always take care not to touch the surface, not to put it somewhere to get the surface contaminated. Also, you should always have a closer look to the sample, so you should check if there are maybe some bubbles inside, or maybe there are some unsolved materials. So just to make sure that the fusion process and the recipe is fine. After this, you can mark the sample. You can put a sticker on it. You can mark the sample. And typically the fused beads, if you prepare standards, you would like to store them for a longer time. We store them in this little box and put them in an excicator that they can be used for a long time. And typically you can use them for years. If they get old, they do not look very shiny anymore. Maybe you can see this in the camera. And sometimes they also start crystallizing. Then they're not usable anymore. So how to clean the crucible? So if the recipe is fine, if the sample is fused correctly and everything works perfectly, the crucibles are more or less quite clean. Maybe you have 1 or 2 drops inside. It's very easily to clean. One way is just to use a pure flux, put it inside and just rerun a fusion. So it's just a cleaning fusion process. This is what you can do. Or you can just put them in some distilled water, and we just clean them in an ultrasonic bath for a few minutes. If the crucibles are more dirty or you have more material inside, you can also add some citric acid to the water and then run it into the ultrasonic bath. That's all about the crucible. So now in the next step, we will go to our devices, and I would like to give you some information about small spot analysis and mapping. So hello again. Now we are here in our demo lab in Karlsruhe, where we all do have our systems here available. This is the S2 Puma, our energy dispersive tabletop system. In general, the system is available with different configurations. So we have a single manual system. We have one with an auto changer, with an XY table and a grabber. And this is the carousel one. This I would like to show you now. The system is quite flexible. So if we talk about very small samples, but also very big samples could be analyzed with this system here. I would like to show you a few samples. First of all, the system is available with a 12-position tray and also available with an 18-position tray. If we talk about small samples, so we have different samples here. You remember this one with this little pigment dot. So if we have samples like this with a small amount where we only make a pressed pellet, so here we do have different sample holders available. This one, for example, to only analyze the small spot. If necessary, we also have different inlays for different diameters available. Of course, for a small sample, we always need a different sample holder, but of course, we also need a different collimator mask. So here, for this system, we do have different masks available. So the 34 millimeter mask is the standard mask, which is used for 4 centimeter samples in diameter, of course, but we also do have 28 down to 1 millimeter spot size. The system is also available with a camera, so you can have a look, a picture of your sample, and you can also have a look where the samples are analyzed. There are different shapes which can be analyzed. Little plates, for example. Here we have a coating on the plate and where we can have some areas. But what to do if you do not have different sample holders, if you do not have different masks? So in any case, if you have very small samples, here I have a little metal piece. So in any case, you can always use the liquid cup, put in the sample, and you can analyze it with a big mask. Here I have another example we have analyzed, a very small metal piece. This you can also fix it, put it to the liquid cup. You can also fix the sample. And in any case, you can analyze these kind of samples. Of course, in the evaluation, you have to take this to account that the sample area or the measurement area is not fully covered. And also, this will have an effect on your results. What about big samples? So here with this carousel configuration, we can remove the tray. I will do this now. So now we have the big chamber, which can be used to load very big samples. So for example, like this metal plate. So this is a zinc-coated plate where you can also check different areas or scratches. There is also the possibility to load smaller plates. So this is just the Lego plate, just an example where you just put the plate into measurement position. We also do have the request for maybe some solar panels, which can also be put into measurement position. So in any case, there's also the possibility to have some sample holders designed or some stages where such samples could be loaded if you really have if you want to run this frequently or as a routine sample. So we talk about sample holders. We do have also some dedicated sample holders which can be used. So in case of filters, we also do have this 2-part sample holder where a filter can be just put in and fixed easily by this magnetic ring. But we also have dedicated designs. This is a sample holder which is used for wires or can be used for little plates. So you can put in little wires next to each other. You can fix them with this magnet, or you can also load different plates. So in any case, there's always the possibility to design, to have some custom-made holders. And so in any case, this can also be used to analyze very big samples which typically do not fit in a sample cup. So that's about big and small samples. And of course, for the SA Tiger, we additionally do have a mapping position. So if you really want to have a one spot analyzed on your samples, so there's also the possibility to have a mapping tool included to the software. Thanks a lot, and let's go back to the studio.
Yeah, thank you very much, Renata. And now we are here back in the studio for our Q&A session. I believe we received a lot of questions, right,
yes,
Frank?
Yes, indeed.
And Renata will also join us in a few seconds to help us answer these questions as the application expert here.
Yeah.
So maybe while she's coming over, you can ask the first question or so.
Yeah, sure. So thank you very much, first of all, for your active participation in our webinar and answering already question already some of topics you are interested in. So, for example, for liquids, one question is here, what's important if you only have a small amount of samples for liquids? How to best deal with that?
And there's already the experts.
Hello.
Did you hear the question?
Yeah, just shortly. So it's about
small amounts of liquid samples, and for example, one of the things has been asked there, can I dilute the sample with a blank and do the calculation later?
Yeah, exactly. So there are different ways how to handle small sample amounts. So first of all, you can use a small liquid cup, like already shown before in the lab. But there's also the possibility to have a bigger cup. At least for a 35 millimeter cup, you should have 1 or 2 milliliters of liquid to cover the measurement area. If it's less, of course, you can dilute it with a blank sample, but then you have to make sure that the dilution is not too high, that you're still in the range of the analysis, and that you're still able to analyze your elements of interest. And of course, the dilution is calculated by the software. So in any case, each dilution with a blank sample, or also for pressed pellets, for binder, amount of binder, this is always calculated by the software. You just put in manually the amount which was used, and then everything is calculated.
Mm-hmm. Yeah, there were quite a number of questions related to particles in liquids. So how about a suspension? How to deal with solids particles which start to settle down during the measurement? One question was related to used oils, which seems to be a topic here.
XRF, yeah. Mm-hmm. Okay, so this is a general issue. Of course, we always would like to have a homogeneous sample in XRF. Doesn't matter if it's a powder or a liquid sample. For powder, of course, you can homogenize the sample by grinding the sample, but this is also a limitation by the grinder itself. And for liquid, of course, you could try to filter the sample, but this is typically not what you want. You want to have the whole composition of the sample, and then the only thing you can do, be fast. So first of all, you can try to homogenize the sample as good as possible, yeah, by a stirrer or maybe manually just by shaking. And then also for some samples like edible oil, it helps to heat up the sample, maybe at 50, 60, 70 degrees. It depends on the material itself. And this will also homogenize the sample. And then the only thing you can do to preparate the sample directly into the liquid cup and start the measurement immediately. So to keep everything short, the process. And what also helps quite a lot is to reduce the measurement time, especially for energy dispersive systems. It helps them maybe only to have a measurement time of 30 seconds. Of course, the statistic is a little bit lower, but typically the effect of sample preparation is much bigger. Maybe one short hint, to see how good or how strong the effect of the sample is, you can just use the same sample and analyze it again in the same cups, but this will only work for energy dispersive system due to lower power. For big wavelength dispersive systems, it's only possible to analyze the liquid cup only once due to the higher power, and otherwise the sample is stressed and the foil is stressed. Yeah.
Mm-hmm. There are also a number of questions for pressed pellets, so maybe we cover a few of them there. So what is the best ratio of wax and sample, and how to calculate the concentration then? How to prepare, for example, zinc oxide powder and samples with activated carbon, in example?
Okay, so there is a wide range of materials, so there is not one recipe that works for all, but in general, for the most material, 10% of wax as a binder is a quite good start. So it's mass percent, so I use maybe 9 grams of sample and 1 gram of wax and mix this. For some materials which are maybe not really stable after this procedure, the easiest way is to increase the amount of wax. So you can start maybe 1.5 gram or 2 gram to increase up to maybe 20%. This works quite well also for some, let's say, tricky sample. So this is one way, and the easiest way, you just have to test it. Yeah, so this is one thing. For what about the
zinc oxide and activated carbon?
So this is the same. So for other materials which are difficult to press, increase the amount of wax and just test it. Mm-hmm. Typically, wax is the best binder. Yeah. So if you use something other than wax, maybe some borax or something like this, maybe then you should try to use wax if possible, because wax has better binding capacity. For very light elements, it's also sometimes difficult, especially for coke samples, activated carbon, black mass, something like this. Some of the materials are even analyzed as powders, yeah. But if you want to have pressed pellets, then also again for coke samples you increase the amount of wax. So sometimes we use 5 grams of coke plus 1 gram of wax as a binder. For very light matrices or like this carbon activated wax will not really work. In this case, we use a liquid binder, which is called Moviol. This is just a powder which is diluted into water, or some use acetone for dilution. And then you take a few drops, maybe 10 or 20 drops of material, mix it manually with the powder, and then you can press it. Typically, these samples are then sticking to the pressing tool. So in this case, you can use this little I got them here, these little foils to make sure that it's not sticking to the pressing cup or to the pressing tool. This helps. So in this case also the reduction of the force of the pressing force helps. So typically light elements are pressed with maybe 10 or only 50 tons. So this is also something you have to just have to figure out on your press and on your tools, just which is maybe the best force to be used.
One participant is dealing with powders which are hygroscopic. So how do you best with such things? And the next question is in the same direction, if they are semi-liquids. So what can we do there?
I mean, for hygroscopic powders, the only thing you can do to dry and to keep the whole preparation process fast, not to get the sample somehow on the desk for hours. Yeah, to keep it fast, and this is the only thing you can do. For semi-liquids, or let's say something like slurries and sludges, the easiest way or the most common way how these samples are prepared are really to get them in a liquid cup and to run the analysis. But for these samples, they're very inhomogeneous. Sometimes you have big particles inside water or maybe some organic parts, and this makes evaluation quite difficult. Yeah. So it depends also a little bit what is really the aim of the analysis. It's more to get a screening, or do you want to have highest precision? For such kind of materials, sometimes drying could be a solution. So you can dry the sample to get a powder. You can grind the powder and then run the sample as a powder analysis or as a pressed pellet, for example.
Another question is related to ore samples. Is there anything important or good recommendation you could give there?
As pressed pellets?
Or,
yeah, I mean, in general, ore samples are not so critical to be prepared as pressed pellets. So you just grind the sample, you just add some amount of binder. So typically also 10% wax should be enough. And you can press them at maybe 20 tons to prepare a pressed pellet.
Yeah, there was a question related to sodium chloride as crystalline white solid. So what's the best way in XRF identification testing?
That's normally pretty straightforward. I mean, you simply use the powder and put it in a liquid cup and measure it.
Exactly.
Because it's if you for identification purposes, or even maybe for some contaminant levels, it's a quick solution. It can be done standardless. You don't even need to calibrate there.
Exactly. And this is a quite common application for XRF.
So maybe we head over to a few speeds. One question is related to the LOI correction. What exactly is that, Renate?
Yeah, so for few speed samples, some samples are ignited first, and also by the fusion process. So in general, CO2 is just escaping out from the sample. So you lose CO2 in your sample. This is mainly a dilution effect that you have to take into account by the software. So this means the sum of the sample will change. So you can use ignited or non-ignited sample. You can define this in the software if the calculation of your calibration standards or of your sample is as ignited or non-ignited. In general, there are different ways, or there are two ways to handle this, but this is mainly done by the software. So the user will define how the sample is prepared. The LOI can be added also to the software, and then the calculation is done automatically by the software.
Perfect. Time is proceeding quite quickly, and there are a number of more questions. Maybe one final question related also to few speeds. What do I have to consider if I have to measure thin ores or chromium sand? And I think this is all related to the crucibles, how to protect them. Maybe a few words there for this last topic.
Yeah. So some of samples are really challenging to make nice fused beads without destroying the crucible. Yeah. So there are chromium ore samples maybe, or ferroalloys are very typical, or some other materials. So in general, these kind of materials, they require some oxidation steps. The temperature of the oxidation steps depends from the materials itself. Also, you will have a temperature ramp for these kind of materials, and typically you only maybe use 200 milligram of sample or 500 milligrams. So also the amount of sample is reduced compared to, let's say, some cement samples or rock samples where you maybe use 1 gram of material. Some additives are required, like oxidation material, and also maybe different fluxes. But this is, again, a wide range of materials. They all have different recipes. It also strongly depends on the system you are using, if you have a gas system or an electrical device. So therefore, even for the same material, you will have different recipes depending on the system itself. So in this case, I will really recommend to contact your fusion experts from your fusion device supplier, and typically they will provide you the right recipe to also fuse this kind of challenging material with a very good quality. Yeah.
Maybe I use this to wrap up a little bit. So you've seen in this hour that we've covered a lot of topics. So sample preparation in XRF is a huge field. Some samples are quite easy and straightforward to prepare. Yeah. You just put them in a liquid cup, or also pressing is really straightforward. Others are more tricky. We can provide advice where needed. One comment here I want to make is that what matters a lot is the right sampling, so that you have representative sampling. And that also, when you have more complex or easier preparation procedures, it doesn't matter. It's good to write them down properly to make sure that you always do it in the same way, because otherwise you're introducing systematic errors. So this is maybe often the most important part, that you do things always the same. And maybe one last comment, we've seen a lot of questions that basically go in the direction, well, how easy it is once everything is set up. That's very easy, because the software also helps you a lot. So let's say you weight a bit more wax in this time, and next time you can enter that, if it even has an effect for you in the software, and the software will do the calculation. As usual, we have a lot of questions, so we didn't cover everything. We will follow up. You will get the recording, you will get the slides, and you will also get a Your Question Answer document, which covers some of the most frequently asked questions. And I think with that, I want to thank you for your time, for your attendance. I want to thank Renata and Frank, and I wish you a great day.
Thank you very much.
Thanks a lot.
Bye.